Okay, so are we rolling? Okay. Welcome to this afternoon session, Saturday, in the 2011 Extraordinary Technology Conference. Briefly, Harvey Fiala is part of the family. He's the father of our technical director, and we think his kid turned out pretty good. Harvey has been an electronics engineer for ages and ages, and he has put together some of the best presentations we've ever seen in this conference series. So I'm excited to hear what he has to say right now. Let's welcome Harvey Fiala.
Thank you, Mike. Most of you probably know me. I've been at more than a dozen Tesla conferences, and I've spoken 2 or 3 times on inertial propulsion, not the last 2 years, but now I got to see if we can get my first slide up. Okay, I'm going to explain first off what inertial propulsion is. It's moving an object without a propellant, like a rocket ship, without a propellant. And another way to say it is moving an object without a reaction against something external. It can react, if this is the vehicle or the chassis, it can react against something within its own chassis. And the secret there is that in one direction some object has full inertia, and in the other direction has little or no inertia. That's the secret to reacting something against something within your own within the chassis. Let's pretend that this table is a 20-foot boat floating in the water. Here's the front part of the boat, and that's the back part. And let's say I weigh a couple hundred pounds. Let's say I walk to the back part of the boat. What's going to happen to the boat? It's going to move forward, right? It's a reaction to me. If I'm moving this way, the boat's going to move that way. Now, let's say I have a magic knob. I can't turn my mass down to 0 because you can see I'm here. But I can turn my inertia down to 0 if I'm smart enough now. But if I turn my inertia down to 0, now I walk back to the front of the boat. What's going to happen to the boat? It doesn't move at all because the mass that it was reacting against had no mass. So the boat didn't move at all. Now I turn my inertia full back up, and I walk to this side of the boat. I actually got it reversed. But the boat moves this way, and then when you stop in the next cycle, it moves more. It never backs up. And that's the secret to inertial propulsion within your own vehicle or chassis. Okay, I'm going to just say a word about, I finally got a patent application. I applied for a patent 3.5 years ago.
Here's your pointer and your mouse. You got to back up, no. Use the arrows.
Okay. this is the better arrow.
Yeah, that's the better laser pointer, theoretically. Oh,
Okay. Well, I'll see if anyhow, they're supposed to have a procedure for speeding up a patent, what's called an accelerated examination. And button, okay.
There's your presentation.
Yeah.
Oops. Hold on. I'll start it.
And they're supposed to give you a patent within 12 months after you apply for it. That's based on age and health and other reasons. And so they granted me an accelerated patent, but it took only 3.5 years to get it. And they have, in the old days, they used to grant a patent on something if you called it inertial propulsion, but now they have hundreds of thousands of patents in their database, and they could call it up, and they're more careful. So they would not let me actually use the word inertial propulsion in the title of my patent. And that's a copy of the front page of the patent. While I'm there, if you look in the upper left corner, you'll see that there's 3 inventors listed. There's myself, my son John, and his son John Arthur. And while I'm on that subject, I might say that my son Andrew is also here, and my grandson Joey is also here. So it's sort of a family event coming to these things. And that looks like a pretty simple device, doesn't it? You might say that it has only one moving part, namely an axle that's spinning with a rotor on it and with a motor on the same axle. And the only moving, actually the motor spinning on the axle, but the axle goes round and round in uniform circular motion. During the first half cycle it precesses. You notice this is only a half ring there. And so for the first half it precesses. It doesn't drop down because it's precessing like a toy top. Then, without stopping it, I won't let it precess anymore. I use a little traction device to scoot it over to this end at the same speed. So it's traction, so it's inertia, it's precessing, tractioning, precessing, tractioning. And when it goes 180 degrees in one phase and 180 degrees in the other phase, the motion ends up in one direction. And in my original patent application, I covered too much. I had what I call horizontal motion. I call it HMT, horizontal motion by mass transfer. And I had vertical motion, and they said that was way too much. And so I actually cut it in half. At first, I have 54 figures in this patent application, and they said you have to break that up into like 23 different patents. And I says, no, that's not. Each additional picture is just to show a slight improvement on the preceding one. And so, but they made that, they stalled that for 1.5 years, but finally we got through to it. And so the whole application contains a tutorial on horizontal moving devices and vertical moving devices, and all the language that goes with it. So it's a tutorial, and there's copies out on the table out there for those who are interested. Now, okay.
Right here, John Arthur? Right.
Okay, it should advance now.
Yes, sir. Here's some more for you also.
Okay, you saw the original one. There's the original one, the simplest one that I could conceive of. And it looks kind of simple, but these equations, it's harder to build than you think. Those equations show how to calculate the diameter of the diameter of the spin axle. And if you do that right, then when you precess around and the traction around, then it's uniform circular motion, UCM. And so it's not as simple as it looks, but that shows how tricky the math can get on it. Okay, there's an example of the vertical motion unit. I have a second patent application pending right now, and I hope they wouldn't grant me an accelerated exam on it because they looked at the first one, but they blocked it once and I've unblocked it. But I hope to get that within a year from now. Now, where do I point this at to get it to advance? Okay, there I want to show you there's a corridor there with 10 solid-state gyros on it, accelerometers. And the purpose of that is to show you that 50 years ago, I actually worked on an accelerometer. And it was this big and it weighed probably 50 or 60 pounds. And if you dare drop it, why, it's gone. Here, you can subject those to 100 G shock and it won't damage them. It might even keep performing during the 100 G shock. You'd have to register the shock though. That obviously limit its output. And here is here's a different version of the simplest one. It's just the next step. In case it fell out of precession, there's a safety ring there, a support ring. But here's the traction ring. This is another version, more complicated. I won't dwell on each of these. And here's here's another version with the rotor inside of the traction ring. The rotor's inside the traction ring. And here's another rotor. Here's another version. It's actually two different decks. One is upside down compared to the other, and it saves they're interleaved. Like you can see that this rotor's on the first deck, that's on the second deck, and they won't bump into each other. So it's an efficient arrangement. And here's another version of it. We won't dwell on the different versions. Here's still another version up in my title there. 2 one-rotor decks with stacked. There's 2 decks stacked instead of interleaved. Two deck, 2 rotors. This has it's a 1 deck, 2 rotor. And this is a 1 deck with 2 rolling pin rotors. What I call, it turns out that if you instead of having a big round rotor, if you make the rotor longer and smaller, but so that it has the same mass and approximately the same moment of inertia, it turns out that I call it a rolling pin rotor. It has improved qualities. It can go faster. And if you end up having a nano rotor, which this whole assembly could be like on a silver dollar with nano rotors, and the nano rotor will get a speed which is the square of the velocity that you would use with the regular. So the nano future of these is pretty good. And here, that's 1 deck, 2 rotor overhead traction. Here's where the traction ring is overhead, and so you don't need a little called buffer wheel there. This is 4 rotors on 1 deck. That's a very efficient way to do it, and that's if you really built a unit. This is for vertical motion. No, this is for horizontal motion. If you really did it, you would use at least 4 rotors just for compactness. You'd probably use 6 or 8 rotors. And here's 4 rotors on one deck with gears. And here's 4 rotors on one deck. It's an underside view. These drawings were done with 3D SolidWorks. And and here's 4 rotor decks, 2 4-rotor decks stacked. So you get 8 rotors. Now notice how they're interleaved so they don't bang into each other. And that lowers the overall height of it. And here's, this is a solid disc rotor, and this is a thin rim rotor, a thin rim rotor. Actually, it has to have some spokes or a very thin disc inside to hold it together. But according to my own analysis, a thin rim rotor, if it is ideal, could lose all of its inertia, which is ideal. It has a higher quality factor. A solid disc rotor could lose only half of its inertia. And here's the very earliest device that I built and tested. This is just a drawing, but it moved. It precessed forward only 60 degrees, then was moved back by traction 60, forward precession, backward traction, and it moved along in a jerky fashion, but it basically proved the whole concept. That was the first. And here's a very simple. If you take a toy gyro, let's say it has a 1-foot axle. And it's just spinning on a pivot point, no motor. It's spinning and it goes round and round. It's precessing round and round. Gravity acts downward and produces horizontal motion of a mass. Now that's very tricky. Most scientists nowadays will say that you cannot use a downward force to produce horizontal motion. And if you use precession, that blows that argument totally out of the water. Now, if you're simple-minded enough and you precess from here, if you have I'll say a 1-pound weight, and you go from here to here, you gain 2 feet. But if you let it precess all the way to the beginning, you've gained nothing. So the secret is you have to precess one diameter and then do something different. You have to give it back its inertia and you have to traction it back. And while you move it back with full inertia, the chassis moves forward. And then you precess, and then you traction it back. So you keep advancing. So a single unit will act. Okay, the purpose of that is to show that right there, that's a simple gyro. It's moving from this point to this point, and if you remove the support or change the pivot point, it goes from counterclockwise to clockwise. If you're smart enough to keep that up, you can go in a linear direction. But that's too hard to implement. But it's just to prove that you can move mass in one direction only with the gravitational force. And once you in my devices, which use uniform circular motion, half of it precession, half it traction, you get a sine wave type. When you have full inertia, you get a big motion. When you have reduced inertia, you get, and it's the difference of those two that give you a net forward motion. There's just more waveforms. You can see that on the top one, for example, you can see that if you have 4 or 8 units ganged together and phased right, you get fairly uniform velocity. And the ripple factor is down to plus or minus 3.3%. And if you use springs or hydraulic filtering on it, you'll have very smooth velocity. And this is just another waveform showing the forward velocity and the rearward velocity. Here is the first diagram of one for vertical motion. Well, this stand isn't needed here at all, but to help orient your senses toward what's up and what's down, I show it on shock absorbers, but it's got a motor, a torquing motor here, which spins it round and round. And when it torques it, these devices would normally go in a circle, but when you torque it, it'll precess upward. the, the axle with the weight will slowly precess upward. It reminds you of Dr. Lathwaite's experiment where he took a 30-pound rotor on roughly a 3-foot handle, and that rotor was spinning at 2,000 RPM, and he picks it up like this with his full weight in his left hand, and his little finger was on the right hand of the shaft. And once you start to torque it, then its weight actually disappears. It makes it look like, well, its weight starts to disappear. It's really the inertia that disappears. And once you start to torque it, the weight disappears, so he was able to lift it, and he's got to keep torquing it with his finger. And if you torque it like this, it'll go overhead all by itself. And then once you torque it up to 90 degrees, which is the maximum for vertical precession, it torques on the inside of a hemisphere. Once it gets to 90 degrees, you can't go any further. If you want to raise it higher, you have to reset the base. All the weight comes back. And that's one thing that most people don't realize about the Lathwaite experiments. There's the same thing with 4 rotors instead of 2. There's, this is a configuration where they're separated enough so they're independent. And I've labeled it the FVSD, the Fiala Vertical Space Drive. And here's one with RPR, the rolling pin rotors, which would give it a higher velocity. And here's one with 2 4-rotor decks stacked. That just, the more rotors you get, the more so-called horsepower you have. And here's, you can stack them vertically, or you can bolt them to the same plane. And here, just in this example, if these are going this way, they actually put a torque on the chassis. So a neighboring one, either above it or alongside of it, has to be torqued in the other direction so the torques cancel and your vehicle won't start spinning around. And that uses 2 stacks, each with 4 rotors. A similar type thing, simpler one. And here's still a more complex one oriented for vertical movement. As you see, they all have a base with shock absorbers on it, which wouldn't be used in real life. And something like that would be used out in orbit. That's another complex version of it. And here, that basically elaborates on the basic cycle. There, when it's down and you torque it, it starts to lift. And when it gets up to, and I design it so it'll go from minus 30 degrees up to plus 30 degrees. And then you reset it back down to minus 30, then precess up to plus 30, then you reset it back down to minus 30, and that's the cycle that it goes through. There's just more waveforms showing the various parts. I used to do a lot of experiments in engineering labs, and we had to write good lab reports with curves and take data and all that stuff, so hence I'm data intensive here. Just more curves. Now here's a very special pivot point. This pivot point will allow, if you come in here, if there's an axle out here with a rotor out here, it can move up or down without interfering with the one at 90 degrees to it. And so each one can actually move more than 60 degrees in either direction without bumping into each other. So that in itself is a little patentable pivot point. Here's a picture where you have 4 rotors and they're all interleaved. An interesting thing about this is that they all have a common pivot point in the center of that column. And the center of that column is a very special point. It can be hollow. That column could have wires or cables running through it. But at one point, it's the spin axle, it's the center of precession, and in this case, the precession is up and down about that pivot point, and it goes round and round in the horizontal plane about that. That's one common point. And so everything, there's perfect symmetry about it. There's nothing out of balance. Now here it's intended like this. It's intended to show that this vertical motion device can be used for horizontal motion. Now at this point I'm going to stop and say that horizontal motion device, the HMT, needs gravity, so it's good on Earth. And a super application of it is if you're rich and have a Lamborghini and you're going uphill on icy roads and suddenly you lose traction, and so you're just spinning your wheels, you could shut the engine off if you wanted to and push the IPD, engage the IPD button. An inertial propulsion device, which is under your hood or in your trunk or something, the car starts moving slowly back onto the gravel road or something, and you can shut the IPD off and put your device in gear again. Now, this here is intended for where there is no gravity, like in orbit, for station keeping applications. In a station keeping, if it drifts to one side, you can use this to move it right or left. You can use it to move it forward or backward, or up or down, or to change the attitude azimutally or in elevation, or there's three axes. You can use it to change along any and tilt like this. And it doesn't take any propellant. There's no jets involved. All it takes is a solar cell. The solar cell has to collect the energy to power a motor that drives the torquing mechanism on it. There's also a motor for each of the rotors, and those are driven by current from 3 minutes left. Those are driven by current from the motors. Now here's thank you. This shows where you shaped pulses to get an acceleration instead of just constant velocity. And down here, I'm going to go to the next slide. This shows a simplified version with 8 nanorotors, which gives you a much higher velocity. And here's another version with a bumper to keep it from bumping into stuff if it moves to the side. Here's one with 4 decks stacked. And here's one with the simplest 4 rotor decks stacked. And here's more the same. Now here is here's where the rotor's inside the control ring. It's a little different configuration, but unless you're going to produce them. Now here's one which has a gimbal on it, so that if your car or your vehicle, your spacecraft is changing in elevation or angle, this axis can stay perfectly horizontal. This takes care of your pitch, and anyhow, here's one where the motor is near the rotor. And that was one where the motor was near the center. And here's one where the motor's at the center. That's the most desirable because the motor chassis is not spinning, and so it contributes no angular momentum to the active device. Half of the angular momentum is on each side of the pivot point. And this is one uses a cone-shaped rotor. It's a thin rim rotor, so it has a higher quality factor. And this is actually kind of a joke. It shows if you use a conical rotor inside of a spacecraft. This just shows the electronic, everything combined into one ring. It's called a control ring. This here accidentally got turned sideways. It shows actually the latest concept of one. There's just one continuous ring, and you tilt the whole ring at about 1 degree angle. And for part of the time, it's crawling uphill in traction, and for the other half, it's floating in precession. So it's a simplified version, which would be superior. And here's an interesting thing. This shows that as you approach the speed of light, your mass becomes infinite. And most of the scientists haven't examined it yet, but after you pass infinity, the mass starts dropping off. And if you can get past that point, then the mass drops way down, which is very good. Now here's kinetic energy. This shows that once you get above the speed of light, the kinetic energy drops off, but then it starts up again. Now that's bad news. And here again, I'll see if I've got another slide. No, I guess that's just about it. There's something else I was going to mention. Well, I think that's it. If there's time for questions, yeah. There's a half a dozen copies of the patent left out there, and as I say, it's got a tutorial in it. And for anyone interested, this is your chance to pick up a copy.
Okay, you've got 5 minutes for questions, and with that, Mark, I've got to cut you off. You're halfway through asking questions.
So, having to know that caveat, I'll turn it over to our question moderator.
Yes, hello. Could you please explain the basic concept of what it is you've done here and why the thing moves? Because I don't get it.
Yes, actually, I went through that. If I'm, let's see, if I'm here, and let's say this is the front of the boat, and I walk here, I'm moving backward, the boat's going to move forward. But now I turn my inertia down to 0, which I can't do, but I can build a device that reduces its inertia. So when I walk back to the front of the boat doesn't move backward if I have 0 inertia. And so that's called one cycle. If you repeat the cycle, the boat moves so much each cycle, and if you have units that are working phased properly, then the boat moves with a steady state velocity.
Okay, I still don't get it. So you're using a rotational motion?
Yes.
And so how does that rotational motion create a directional motion?
If I'm precessing like this, just a moment. If I'm precessing like this, the bone will move backward a little bit. But then I'm not precessing the other 180 degrees. I'm going with full inertia. And when I go like this, then the chassis moves forward a big amount, see? So it's precession, traction, precession, traction, precession, and it goes in, the thing doesn't stop each time. It switches over from precession to traction quietly, and the motion is uniform circular motion. So that's the principle.
How do you switch from precession to traction? Is it I don't know.
Pardon?
Where do you make the change from precession to traction?
Okay, when that precesses from here, it's in the air. As soon as it touches this semicircle, that supports the axle, that supports the rotor, and a supported rotor won't precess anymore. In order for it to press, you have to remove the support and it'll stop. So I stopped from precessing with this traction ring here. Half a ring, yes. And in later versions, I put another half a ring a little lower down as a support ring in case I don't want the thing to fall and get busted. We talk later on. Ask me all the questions you want.
Hello, my name is Frank. When I was in college, I designed a similar thing, except where you have a gyro,
Yes.
I had two half gyros, like an orange cut in half, spin in an opposite direction to negate the centripetal force of the spinning thing. And I'm wondering if you had considered something like that and how affect that would
I've
happen.
studied configurations like that, and you won't get a reduction of inertia in any particular direction. And it's a very interesting device, but
No, but you'd eliminate the gyretic torque that tends to throw everything out of whack.
it will not produce any propulsion. And to explain that to you, we can do that offline.
Actually, that one takes a few more minutes than we have right now. But in closure, ladies and gentlemen, think about this. Something that looks like an aluminum Dristan capsule, maybe about 12 and 3/4 inches in diameter, about 27 inches high. You lay it on a little Lionel train. It's got one insulated contact and a little antenna on it. You engage your remote control, and it begins to motivate down the Lionel track. You shut it off, your remote control, and it stops. You can take that thing and reverse the polarity, and it backs up. Now think about this. You set it on a scale, and you begin to engage it, and the scale begins to gain weight. Now you take this thing, in this particular case, you'll have to turn it upside down because that hasn't been, because the one that really does the job is perfectly round and has to play into exactly what you were saying, two contra-rotating. But turn it upside down, then re-engage it, and all of a sudden the scale begins to lose weight. Imagine that. This is the inertial propulsion realized. Harvey Fiala. Thank you very much, gentlemen.
Thank you.
Okay, we're going to take a short break. We'll see you back here in about 10 minutes.